welcome to the second day of the summer school on machine learning for electron microscopy. My name is Gerd Duscher. If that is your first day with us, I have put up our schedule. So today we will do diffraction, electron diffraction, and our participants are very diverse. A lot of them are experienced microscopists. Many of them are data scientists, and they all have to be brought to about the same level of understanding, at least of vocabulary, right? So I always say science is about 90% the language course. So we are starting with introduction to diffraction, and we will go all the way to 4D STEM and how we can analyze that. So Colin Ophos from Stanford will be being our first guest speaker in that machine learning course here. So let's start. As usually, I have no problems with getting my stuff done. I'm restarting my thing. So if you haven't been here, let's go back. Under resources, GitHub repository. We are on day 2. And so if you go to basic diffraction, you can follow that on Colab if you just log on to that. Okay, we have the first problem here. It's not super. What is the problem? It's an old version here. Basic diffraction. Okay, mine doesn't allow me to. Should be working. Okay, I'm not sure what's going on. I hope you have better luck on that one. You might have to copy it over and do that. So the whole lecture is based on no. Okay, we'll have to figure that out later. I'm sorry. So we're gonna have to move on. We have a big program here ahead of time. Maybe some of my students can look into that. Okay, we'll check on that and get you going as soon as possible. Okay. Good. Thank you for the fast feedback here. Where is my chat? Is it there? Okay, good. So the diffraction is based on PyTemlib. PyTemlib is a part of the microscopy ecosystem. The microscopy ecosystem also has asynchroscopy, so that is the remote server software that we're using and used yesterday. So all of that is in this microscopy project on GitHub, and you can just download it and use that, no problem. While I'm at it, every Friday at 10 a.m. Eastern Standard Time, we have a hackathon on microscopy. So if you guys or any of you want to participate in that, that would be nice. We will send out the Zoom link if you want to. So, okay, so we loaded the PyTem version. It's always a good idea on these notebooks to see what kind of version you are operating with. So let's go here and look at the basis of any diffraction is, of course, Bragg's law. All of us at some point or other have learned that, right? 2D sine of theta is n times lambda, and in which the d in our case is interplane spacing of the crystal. Theta is the Bragg angle and lambda is the wavelength. Since our wavelength is very small, we have diffraction on crystal planes like with X-rays or with neutrons. Why also there are no atomic resolution microscopes based on neutrons and X-rays? They don't have lenses. So the only thing that is good for ions is in favor for one of the things that is in favor for ions and electrons is that they're charged, and so we can have magnetic lenses. The path difference between one plane and the other is 2 times this part here, and that is where the Bragg law comes from. So 2 times this extra path length is the key, and if that is coherent, so n times the wavelengths, then everything is at this point in time in sync, and we have a positive interference. The distance of the planes in real space is relatively small, so in reciprocal space, it is relatively large. So we are talking about the reciprocal space, and the G vector is, well, one G vector is has the length of 1 over this distance. So please remember, we are doing it in the material science convention, where we do not use the 2 pi multiplication, right? So we directly go from nanometer in real space to 1 over nanometer in reciprocal space. And now if we put our vectors that we have in real space, the angles don't change. So we come in with our incident beam. Okay, so the Google Colab should work now. Okay, I did a mistype there. Thank you, Austin. So there was a single one, a space apparently. So okay. If any of the links don't work, let us know. We will fix it. So anyway, we have the incoming beams that has a length of this vector, which of course in reciprocal space is 1 over the wavelength, so it's the wave number, and we have an incoming one and the diffracted one. And since it's vectors, you can shift this diffracted wave vector wherever you want to, for instance, in the beginning of the incoming one, and you have the correlation, the geometric approximation of the Bragg's law. And that means that if there is a G vector, then you can just make this triangle. And the Bragg angle is defined as half of the angle between the incoming and the diffracted wave vector. And so we have our Ewald sphere. And the Ewald sphere is for geometric and actually also for calculations, the easiest way to do diffraction, and we'll see how that works. I just wanted to introduce here the Ewald sphere, the concept of the Ewald sphere, so that you know that. So if we have a center, we have an incoming beam, an initial beam and the diffracted one, they all have to lie on the same sphere because they have the same length. So we have elastic scatterings, they don't change. And so I hope this little schematic here showed you how that diffraction works with the Ewald sphere. So the concept of the Ewald sphere will be the basis for the rest of this, at least of this lecture. Okay, so let's go from a crystal in real space. So here is my real space. We have crystal, right? Silicon 100. We'll see it. 100 is a crystallographic orientation. Unit cell. Let's go back. I drew here 4 unit cells. The nice thing about ASE is it has all this stuff. So here we have what's going on here. Okay. So we have a cube, and if we only 001 is basically we don't go we go 0 direct in the x direction, 0 in the y direction, and we go up or down, in this case, up in the z direction. So we look down the face of this crystal, and if we make a few of them, then we have this few. The wavelengths and the magnitude is defined by the de Broglie wavelengths, right? So, and we get this wavelengths directly. So we have 2.5 picometer at 200 kV. We can go to 100, right? So we have 3.7 picometer there, and at 300 it gets very small, obviously. This wavelength has to be relativistically corrected, so we have this relativistic correction. Otherwise, we would have actually classically we would have a speed faster than the speed of light, so that would not work, right? So we are having this relativistic correction in here. So the reciprocal lattice and the incident wave vector. So we need a reciprocal cell. So we have defined our crystal in real space. Our atom positions are defined by the lattice unit cell, by the unit cell of the lattice, and then the base, it's called base, if where you place your atoms within this unit cell, right? So we have a cube, we put our atoms here in relative coordinates all over the place. Crystallography in 2 seconds, okay? So the Miller indices are just how you are defined on the basis of the unit cell, so that unit cell is our coordinate system, and the Miller indices are how far you go in one direction or the other. Unit cell, just as a reminder, is has to stack of all the unit cells has to fill the space completely, so there cannot be any gaps. So if we do, yeah, where are we now? Okay, here we are. So we have a reciprocal cell, and if we plot that cell, okay, it looks like before, so we have no basis here. It's just based on the unit cell, because we're only wanting to look at the planes. So it's one part here, and okay. Okay. And if we make a whole cell out of, also a whole lattice out of that, so also the reciprocal unit cell is going in all three directions for all our purposes infinitely, right? So that is one of the problems people have sometimes. They look in the books and they always are two-dimensional like here, but really it is a three-dimensional lattice. And we have an origin on that, so we just define one at 0. And because this is electron diffraction, and we have not only the 0 order Laue zone, so that is the plane in which the origin of the reciprocal lattice lies. We have also our other Laue zones. So it's called the first order Laue zone, second order Laue zone, third, blah, blah, blah. And most of the time they are just grouped together as higher order Laue zones, faults. There is false rings, false lines, and we'll go into that. So the Laue zones. Laue zone is the plane, so it's just a question in the chat. A Laue zone is a plane, is a plane in reciprocal space, perpendicular to the, or more or less perpendicular to the incident beam direction, okay? And so in our case, it is this plane with all these dots. Hope it's clear. And so the next plane is over here, and it's a real plane, so it's going into the screen here. So we got that covered, and now we do our Ewald sphere. And that's where the difference comes in between what you're used to in X-ray diffraction. That's what most people are used to. And that is supposed to give you an impression of what's going on. This is, the blue one is the Ewald sphere of, how much did I put in here as an acceleration voltage? I didn't see, okay, I forgot, but that looks like about 60 kV, so it's not too dramatic. And does anybody see the X-ray Ewald sphere? We have to zoom in a little bit. This is the Ewald sphere of the X-ray. Okay, there was a chat here. 1 over D? Yes. Okay, so so the Ewald sphere in X-ray diffraction is very small. And in electron microscopy, it's basically very flat. If you want to see a Bragg reflection in X-ray, in an X-ray diffractometer, what you have to do is you have to make a theta to theta scan. And in the following, I want to point out that this theta to theta scan is actually effectively just rolling around your Ewald sphere on in this reciprocal lattice point, so that you will eventually roll around and find and activate one of the diffractions, Bragg reflections. And so the exact Bragg reflection is when the reciprocal lattice vector, a diffracted beam hits one of the reciprocal lattice points. And so you see, if you're perfectly in zone axis, you should not see anything because, of course, there's always some kind of curvature here. So we only hit it in the center, so we have to tilt that. And so we do now a theta to theta scan, and you could do that in 2 different ways. One way is you tilt the sample, and the other one, you tilt the incident beam. That is completely equivalent, right? And you can see that with X-ray, you hit very few, while with electron beam, you hit a lot. And that is just because the Ewald sphere is so huge, so effectively on the sample, it is extremely flat. The precise Bragg reflection, if we look at that, then we have to tilt the Ewald sphere so that we hit exactly one of these Bragg reflections. This is the basis for imaging analysis. Oh, there's something in the chat. We use that in imaging analysis or imaging conditions, so this so-called two-beam condition. And here are chats. Okay. No. That is not. The Ewald sphere is based on the electron beam. And a Lowry zone is defined in the crystal. Okay. So not every, so the Ewald sphere is completely independent of that. So you leave the Ewald sphere alone and you can rotate the incoming beam. That the Ewald sphere stays where you can rotate that, but around the zero origin. But the Lowry zones, I think what you want to say is that the Lowry zones change depending on what the incoming direction is, and that is correct. Okay. Hope I answered your question here, Mehmet. Okay. So if we tilt it so that it hits one of the reciprocal spots exactly, we have a Bragg reflection. Okay, you got it. Thanks. Okay, so we hit it exactly, and here we have now our Bragg reflection. Okay. And now we come to the interesting part. It's excitation error. Because if we look at the diffraction pattern, you will see that in electron diffraction, even if we are perfectly in zone axis, we have a lot of spots. So we get these spots even though we have. Okay. So we activate these spots because we have actually, even though we have a so-called excitation error, pointing up is positive, down is negative. And so this is the deviation between the exact position, exact Bragg condition and the effective G vector or incident diffracted beam. So why can we do that? Effectively, we should never see anything. The key here is, again, thinking in the duality of real space and reciprocal space. A sample, not to scale, looks more or less like a cell phone, right? It's very thin and wide. And how does that look in reciprocal space? In X and Y, it is extremely small, right? And in the Z direction, it's very high. And that's the excitation error. And we go a step further. Everything we find complicated, we can blame on this excitation error. So this excitation error not only has like a stick, it actually has different, it's more wobbly. So it has actually periodicities to it. And so this excitation error is where there is additional information in an electron diffraction pattern. So we blame everything on the excitation error. If we don't want to look at the excitation error, we just forget what's in the, we just make our spot so small that all of them have just one intensity. But if we want to look at the excitation error, we can actually increase that. So we'll come to that. So the excitation error is what gets us additional information. How does it look with just for you guys to get a handle on that or make you start thinking about it? If you have a nanoparticle, how does that look in reciprocal space? First thing is large, right? But it's actually like an onion, right? So you have a core that is relatively large, and then it's a shell, a shell, a shell. And so you can see how in the reciprocal space, wherever you hit that with the with the Ewald sphere, you have now dark and bright regions. And all of diffraction can be done with trigonometry, right? So you always look for where is triangle with the right angle. So apparently we have here one, right? And so everything goes back to that triangle. The other things that I wanted to point out, we have, unlike, okay, I forgot about that, to go back up a bit. Okay, we don't have enough turn here. So we eventually will like, yeah, it's hard to say here. So eventually we also will hit the higher order Laue zones, and in the higher order Laue zones, we see basically a ring because that is very large angles now. So we'll come to that hopefully too. So now we plot. This Ewald sphere. Isn't that supposed to bring us something? So we want to look at all the possible reflections. So what we do is we just make all different diffraction spots, so all the reciprocal lattice points. We have an Ewald sphere, and we can check just how many of the reflections are close to the Ewald sphere. So that's all we do. So we have a mesh, we have a sphere, and we check how close they are. We have a center. We have an excitation error. The excitation error is related to the thickness, right? So the thinner it is, the larger is our excitation error. This simple concept got somebody the Nobel Prize. Was actually Geim with the graphene. So that was how he proved that that is a 2D material. So it was so thin that the excitation error was extremely large. And so he could see all the diffractions. And even if you tilt them, you always have the same reflection. So that was a proof for that. So this concept is not unuseful, right? So it's a very useful concept. And then we can just check all of these different reflections, see how close they are to the Ewald sphere. Then they have to have a certain distance, right? All we do is we determine where the center is of our Ewald sphere. We determine how close they are, whether they have the right distance. If there's a distance deviation smaller than the excitation error, we take it. End of story. So we have, in this case, we tested about 350 different lattice points. And of those, 2,000 have an excitation error less than what I gave it, 0.03 nanometer, right? And then I can look at the form factor, that is just whether there is a positive or a constructive or destructive interference here. Say, oh, there's a chat. Oh, okay. So how big can, so the question in the, if I translate it into how I was introducing it, the first order of magnitude for this excitation error that is occurring is 1 over the thickness of your sample. So that's where I was going to with the GAIM approximation, right? So if you have 1 nanometer thick sample, then it's 1 over 1 nanometer excitation error. So get smaller. Yeah, so with 10 nanometer, you have 1 over 10.1. The thicker it gets, the smaller gets the excitation error. So I wanted to introduce the form factor. So each atom, I saw that. Okay, I must have skipped something here. I'm sorry. Ah, here we are. No? I'm missing something. I'm sorry if you get. Okay, we'll do that later. So the form factor is the probability for an atom to scatter in a certain angle. And then in a crystal, we have many of those, and we have, so they introduce a phase shift. Where are we here? Possible reflections. So we have the structure factor and the form factor. So structure factor is the assembly of that. I'm not going too much into that. So the form factors are tabulated and the structure factors are, do we have some here somewhere? It's a potential. And then, so in a geometric position or in a consideration, what we want to know is where does the structure factors come from? In the beginning, the lattice planes, so the reciprocal lattice, so all these points are based on the unit cell. With the structure factor, now we introduce also the atoms in the unit cell. Where are they? So we have in reciprocal space, we have all these spots. But the distance from the origin to any atom within the unit cell is much smaller. Let's assume I put it in the halfway between the x-axis of the unit cell, because we are one-dimensional right now, right? Then it is every second one that has an atom, and that is expressed in the structure factor. Okay, I should have put the formula here to get it easier. So anyway, so we calculate how many atoms, we consider all possible reflections in reciprocal space. We check how close they are to the Ewald sphere, and then we check whether they are allowed reflections. That narrows it down, and then we are ending up with 57 out of 350 in the zero order Laue zone. So to visualize that, this is the Ewald sphere, right? And if I'm very good about that, so we see here, okay. So we see the different Laue zones that hit it. The red ones are the zero order Laue zones. So that's what we did mathematically, right? So we have an Ewald sphere, and that's it. Let's zoom out here a little bit and do it without the Ewald sphere. How do we get from that to a diffraction pattern? We gotta tilt it. And so apparently my X and Y are not very, okay. It's very hard to tilt it very exactly. So that's why we do that with, by rotating it, so we can calculate the rotation of the Ewald sphere, right? And get the rotation. So that depends on your directions that you come in. If we come in 100, it's trivial, right? If you come in the 11, 7, 8, so 11 in the X vector of the unit cell, any other ones in X and Y, then we can figure that out. So we rotate that back so that the incoming beam is parallel to the z-axis. And then we have our Ewald sphere on top, and the projection down is our diffraction pattern. Very, this way you can visualize that very easily. We make a mistake when we do that. A small mistake, the smaller, the flatter the Ewald sphere is, because what we really do is, not, in this case, we just project it down, but we have angles, right? And so it's really the cut of a plane with a sphere, right? So it is the projection is a little bit off if we do that. If we want to do it very accurately, then in the first point, you know, so you have to calculate the angle and how it is projected down, or you make your life easy. And making life easy is all what we're all about. We have a sphere, so we do everything in spherical coordinates. Done. Right? All we have to do now is we have to plot set by angle, and when we and the angle on the plane, and we are done. So the projection is not really just setting the C to 0 as I did it here. So to be very accurate, you want to just work with angles and be done with it. Now we go to the convergence part of that. And that's what we are doing in STEM mode. In what we have considered so far. Oh, I'm faster than I wanted to. I have a lot of that stuff extra. Okay, good. Bad planning, thank you. So we have the selected area diffraction. That is when we have a parallel beam, so we have only one direction hitting the sample. Let's assume we tilt the sample a little bit. was a beam in our case, right? Then instead of having the center beam, we have now also this tilted beam. If we have a whole cone of these beams, so beams in all kind of directions up to a maximum, we will get a disk. And that is a convergent beam electron diffraction. Okay. So, and each point in the disk, it's a bit high. Each point in the disk has a different excitation error, right? Because they have different, slightly deviation in the Ewald sphere. So all of them have a different excitation error. And so what a convergent beam electron diffraction pattern is, it is really a map of excitation errors. And in the excitation error is an internal potential. So the crystal symmetry is there. You have all this extra information that you can get to. And so with electron diffraction, you have the same problem as with everything else. In electron microscopy, the electrons interact very, very strongly with your material. Somehow I'm missing a few parts here. And so what we have is I think I have to open some other notebook here. If you give me a moment. So we have, what I want to say is the electrons interact very strongly with the matter. So we are not only scattering once within the sample. Usually we scatter several times. So we get a Bragg reflection. We can then scatter again, get another Bragg reflection. So we get multiple diffractions. Can I have this multiple diffractions from a single atom? And the answer is, for my students, is yes, because they know it, they were in my class, right? So you can have a very fat atom, and before you hit it, you see the potential already, and then within that path of the interaction volume, you can hit it again. You need a very, very fat atom, right? So, but this multiple scattering will happen in even thin samples for most materials. And that means that diffraction spots that are forbidden. Let me go and see. Okay, didn't expect to have so much time, but we can possibly find one. Okay. Yeah. Oh, no, I cannot. Let's do it. Just open one from the PyTemlib. Get rid of. It's a bit, I have this stuff in my way. Okay. Get rid of all of those. Okay. Again, we have to run that. We define our crystal. And we do the same thing we did before. We calculate say, okay, I forgot. This one did not run. Okay. A little bit out of point here. So we plot our diffraction pattern. What we see already, let's do that a little bit higher. We can do a larger HKL. Okay. So what we see now is we see actually our Holtz ring. So the center part is the zero or the Laue zone. And further out are our higher order Laue zone rings. We can plot the so-called Kikuchi lines. You might be don't have a good. It's maybe not the best art to explain that. So the Kikuchi in PyTemlib, everything is directly calculated. So you have the Holtz rings, Holtz lines, the Holtz rings, and the Kikuchi lines. The Kikuchi lines don't need any extra calculations. So all you need is to go in between the center and here, and you already have your lines. So it's relatively straightforward. And so we get the whole picture here in one O direction. It's a And the beauty of the Holtz lines is that the Holtz lines are the Kikuchi lines are directly associated with the crystal. So even if you have mistilt, you can see that, and we'll see in the next lecture, we will do it on the microscope, and we'll directly look at that there. So we will look at the Kikuchi lines. We look at the symmetry of the Kikuchi lines, and the center of the Kikuchi line is where our exact zone axis is. So we can directly find them. If you're somewhere in a random orientation from your zone axis, what you're doing is you're looking for the Kikuchi lines that are the most narrow. They are associated with Bragg reflections that are very close to the center. And so effectively we can navigate with these Kikuchi lines. So the Kikuchi lines are your friends. They make your life very, very easy. So they are like, this is a interstate to the next zone axis. And we can plot the Holtz lines. It's a little bit over the top here. But the higher order Laue zones makes the same thing as the diffracted ones. So what happens here, and I might try to find this notebook from my class, just so that we GitHub. Okay. Diffraction. Should have some pictures here. Okay. So Kikuchi lines And that's why we can use them also in SEM as part of the energy electron backscatter diffraction patterns. They originate in the sample. So what happens is the electron comes in here, in there. It scatters by the phonons in all kinds of directions. And so now you have a source of electrons inside the sample, and they scatter, of course, in all directions. If there is no crystalline material, all you get is a gray background. So these scattered electrons, they don't scatter according to the Bragg reflection. They scatter just homogeneously in all directions. Now, if these electrons hit a plane, they get scattered according to Bragg. And they are scattered in all directions inside the crystal. So that is these two cones here that make you the Bragg reflection. And so you have a deficient line and an excess line. So the electrons that should go to the gray background get deflected. In this case, we do it the other way around, right? So the electrons that hit the plane that should contribute to the gray background don't get there, but they go to the Bragg reflection. And this is exactly the distance is 2 times the Bragg angle. And that is just twice half of what your G vector should be in reciprocal space. So they are in between them. And so we do that here. Run. Doesn't, because we have not selected a kernel. Not sure that works. What planes are here? No, we don't have them. Okay. So anyway, so they're exactly in between, and they are centered in the inside the crystal, and so unambiguously you can determine where a zone axis is. The other thing I wanted to say here in our diffraction spots, so we have our and then I have to so what we are looking for in diffraction pattern is always, this is not a good diffraction pattern. So there are, I must have deleted them, so there were a few more plots supposed to be happening here. So what we are looking for in this diffraction pattern is always symmetry. It is the symmetry, and the symmetry, obviously, if you have a cube and you look down, say, one direction, so you look at the face of a cube, then you see a square. You tilt it by 45 degrees, so you look at the square, at such a cube edge on. Then it's a rectangle in projection. And if you look at that down, say, one of the corners to the diagonal, the space diagonal, then you see something that is a 6-fold. And so looking at the symmetry of your diffraction pattern directly tells you what kind of symmetry your sample has in different orientations, or in the specific zone axis where we are. So we want to see that on the microscope in a little bit. Let's make a 5-minute break and start at 10. And on the microscope, everything is a little bit easier. You can see that directly. And we should have plotted, say, diffraction pattern here. So we want to see the convergent beam pattern in the microscope. And we want to see these Kikuchi lines. Okay. Oh, there is a lot of things in the chat now. Now, if you're in exact Bragg conditions, say, what really happens is a multiple scattering. And so you see the Kikuchi lines actually as bands. So I keep your question here on till we see it on the microscope. Okay. There's another question here from Riso. Tilting. I thought that the crystal should be rotated. Why do you rotate the beam? The point is it is completely equivalent. So whether you tilt the beam and we set rolls this Ewald sphere, or whether you tilt the sample is completely equivalent. In the microscope, of course, we cannot tilt the beam very far, but we can tilt the beam a little bit to get it in the right orientation. So a good double tilt holder will get you to 0.1 degrees accuracy, but sometimes you want to be better, and the last little bit you do with the beam tilt. So a very good question. So for practically orientation matrix formulas that we can use. Yeah, we don't do any of that. That's the beauty of the Ewald sphere. We just put. We don't have to have a specific formula for the orientation. All we really need is our reciprocal lattice, and then we come in. We define a zero position within this reciprocal lattice, right? So plus minus in all direction, and we just tilt the incoming beam, so the center. So if the simplest one is I come just down into the reciprocal lattice. But I can tilt that by 3, 4, 5 degrees, 15 degrees, according to some kind of different Miller indices, right? It doesn't matter where I'm going. And then I just do the same formula as always. I just figure out which reflections are close to the Ewald sphere within our excitation error. And then I calculate the structure factor. Is it allowed or not? Does it have constructive interference or not? If the interference, if it is destructive, it's forbidden, it's gone. So we don't have to do anything special for that. And that's the beauty of that approach. Okay. And once you have all the reciprocal lattice points that contribute in the zero order Laue zone, in all the higher order Laue zones, you can calculate the Kikuchi lines, because all they are the lines that are the intersects. So you go to the reciprocal lattice point in your diffraction pattern, you halve the distance, and it's perpendicular to that line. So that intersect is your Kikuchi line. You're done. You do the same thing with Holz lines. It's a little bit more complicated. I would refer you to my lecture if you want to know more about that. I might have it as a. That's what I should have done to begin with. Under diffraction, we have these Holz lines. Weird orientation, and then it's a lot of trigonometry here, and but in the end you get these deficient lines from the higher order Laue zones. The interesting thing is this high angle diffractions make a signature very close to the center of your beam, so you can. So it's very, very precise. So you can determine the size of the unit cell within a picometer, and so you can be mapped at the time the strain field of strain-enhanced silicon devices. So you can do this kind of stuff by just looking at it. So there's a lot of things going on in diffraction, and we cannot handle it all through. So it takes me about half a semester to go to the basics of that. So I'll refer you back to this GitHub page here. Okay, so that's it from this part. Let's make a 5-minute break. So, do you have anything else? G3G. Okay. You really don't care for the different Kikuchi lines. You will see that if you go to a G3G, so that's when I go to the third order of the Kikuchi lines and put them through the center in order to go in this case, weak beam condition. Probably you see actually when you tilt out that you will have the deficient and excess line very clearly separated in that case.